Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. For part number 7, this part actually the final part for chapter number 6. Still we consider about the air conditioning processes. But in part number 7, we will discuss about the adiabatic mixing of air streams. So in order to understand what is what I call the meaning of mixing of air stream, so we look at this schematic diagram. So let's say we have a cooling section in AHU air handling unit. So we have a room. So the circulated air from a room will enter the cooling section of AHU air handling unit in order to reduce the temperature of the air. And from the cooling section, at the outlet of the cooling section, we will have cool air at certain temperature and also certain humidity. And let's say we have another air ducting line where the outside air or fresh air from the outside will enter the air ducting system, and this cool air from the cooling section will mix with fresh air, and the section that mix cool air and also fresh air together we call the adiabatic mixing of air stream section. And then from this section the mixed air will enter the rooms. The section that circled by the red dotted line is actually referred to the mixing of the air stream section. Okay, so normally we will use the simplified schematic diagram as shown in the pictures, where we have at least we will have 2 inlet and also 1 outlet. So inlets represented by state number 1 with omega 1 H1 T1, and also the state number 2 with omega 2 H2 and also T2. And at the outlet we have state number 3 with omega 3 H3 also T3. Okay, so the dashed line represent the boundary system for the mixing section. Okay, so there are a few reasons for the process. Okay, first, our aim to increase the air quality in terms of the what I call the content of oxygen inside our air that enter the rooms. Okay, so we want to increase oxygen and reduce the carbon dioxide content in our air before entering the room. So let's say, for example, due to the what I call the respiration of the human inside the rooms, so we will have in terms of quality of the air will reduce, where we have more CO2 and less oxygen O2. So let's say the circulated air from a room with less oxygen will enter the cooling section, and the cooling section will reduce the temperature of the air. And now in order to increase the what I call the oxygen content inside the air, so we will suck the fresh air with rich oxygen content into the mixing section. Okay, and then the circulated air from a room will mix with fresh air with rich oxygen content, will mix in mixing section and then enter the rooms. So the quality of the air enter the room from the air conditioning system will increase. The second reason, we want to save the energy for the air conditioning system, okay, for cooling and also heating process. Let's say we need to set the temperature of the air inside a room at 23 degrees Celsius, and the temperature of the circulated air from a room that enter the cooling section is around 30 degrees Celsius. Let's say now we only have one ducting system without mixing section. Okay, so no fresh air from the outside enter the mixing section. So now, in order to reduce the temperature to 23 degrees Celsius, the cooling section need to use an energy in order to reduce the temperature from 30 degrees Celsius to 23 degrees Celsius, which is, if you refer to the delta T, the temperature difference is around 7 degrees Celsius. So the system need to provide a certain amount of energy in order to reduce the temperature from 30 to 23 degrees Celsius. Okay, now let's say we manipulate the temperature of the outside air. Let's say the outside air in terms of temperature already very low. Let's say the temperature of the outside air is around 18 degrees Celsius. So we want to manipulate the cold air temperature from the outside in order to save the energy for the cooling process. Okay, so now this cold air from the outside, or cold fresh air with 18 degrees Celsius, will enter the mixing section. So in order to obtain 23 degrees Celsius, the temperature of the room, so at least the temperature that come out from the cooling section is around 28 degrees Celsius. So if we mix the cold air with 28 degrees Celsius and also the fresh air with 18 degrees Celsius, probably we will have the outcome of the temperature after the mixing will be around 23 degrees Celsius. So if you look in terms of temperature difference, the temperature difference between the circulated air from a room at 30 degrees Celsius and also the temperature at the outlet of the cooling section is around 28 degrees Celsius. So the temperature difference will be only 2 degrees Celsius. So less amount of energy we need to supply in order to reduce the temperature from 30 degree to 28 degree. So this is the example how this mixing of extreme process will reduce the energy consumption for the air conditioning system. Okay, adiabatic mixing of extremes. So adiabatics here means, if you look at the schematic diagram, the schematic diagram shows the mixing section. So adiabatic mixing of extreme means at the mixing section we need to use an insulator to make sure that no heat transfer in or out of the boundary system. So that's the meaning of adiabatic mixing of extreme, where we not allow any heat transfer in to the boundary or out from the boundary of the mixing section. Okay, so if you look at the schematic diagram of the mixing section, so we have the inlet condition. At least we need to have 2 inlet and 1 outlet, where at the inlet we have state number 1 with omega 1 and also H1, specific humidity and also enthalpy, and at state number 2 we have omega 2 and also H2. So at the outlet of the mixing section we have state number 3, omega 3 and also H3. Okay, so if we draw the process on the psychrometric chart as shown in the second figures. So we have state number 1 and also state number 2. So the main criteria for state number 3 will be if we draw a line that connect between state number 1 and also state number 2. So the position of state number 3 will be on the straight line that connect between state number 1 and also state number 2. Okay, so from the figure we can see in terms of the enthalpy difference between state number 1, state number 2, state number 3. Similarly with the value of the specific humidity difference. Okay, omega 2 minus omega 3, omega 3 minus omega 1. For the enthalpy we have H3 minus 1, H2 minus H3. So we can use this relationship in terms of enthalpy and also specific humidity in order to obtain the other parameters for the process. So if we implement mass balance equation, also energy equation, so for mass of dry air, MA1 dot for the first inlet plus MA2 dot for the second inlet equal to MA3 dot for the outlet of the mixing section. Okay, for mass of water vapor, mv1 dot at the first inlet plus mv2 dot at the second inlet will be equal to mv3 dot at the outlet of the mixing station. So if you implement the specific humidity equation, so we'll get ma1 dot multiplied by omega 1 plus ma2 dot multiplied by omega 2 equal to ma3 dot multiplied by omega 3. So if you implement energy balance equation, so you get the equation for E mass in, E mass out, because now we have two inlet and one outlet, so we'll have E mass in at the inlet number 1 plus E mass in at the inlet number 2 equal to E mass out at the outlet state number 3. So we have, in terms of equation, so we'll have ma1 dot multiplied by h1 plus ma2 dot multiplied by h2 equal to ma3 dot multiplied by h3. So from this equation, and also by referring to the simplified psychometric chart above, so we will have a relationship in terms of mass flow rate ratio with the specific humidity difference ratio and also the enthalpy difference ratio. So from this equation we can manipulate the equation to determine the mass flow rate or the specific humidity or the enthalpy for the specific state in the adiabatic mixing of ice cream process. Example 6.7, saturated air leaving the cooling section of an air conditioning system at 14 degrees Celsius at a rate of 50 meter cubic per minute is mixed adiabatically with the outside air at 32 degrees Celsius and 60% relative humidity at a rate of 20 meter cubic per minute. Assuming that the mixing process occurs at a pressure of 1 atm, determine the specific humidity, the relative humidity, the dry bulk temperature, and also the volume flow rate of the mixture, which means we need to determine the outlet condition of the mixing section in terms of omega, relative humidity psi, dry bulk temperature, and also the volume flow rate. And the pressure given is 1 atm, so we can use the psychometric chart in order to determine the important parameter for this question. Okay, now the solution for example 6.7. So first we draw this simplified schematic diagram in order to understand the problem and state whatever data given in the question. So we have cooling section, we have a room. So from the cooling section, at the outlet of the cooling section we will have saturated air, where the temperature is 14 degrees Celsius and the volume flow rate is 50 meter cubic per minute. Okay, so saturated air means the relative humidity equal to 100%. And this saturated air will enter the mixing section, and the fresh air, the outside air, will enter the mixing section at 32 degrees Celsius with volume flow rate of 20 meter cubic per minute and the relative humidity equal to 60%, and then enter the rooms. Okay, so this is the mixing section. So we have state number 1, state number 2, and also state number 3. The condition for state number 1 and also state number 2 are already given. Okay, solution for example 6.7. So this is schematic diagram and also the simplified psychometric chart to represent the general process for the adiabatic mixing process for state number 1, state number 2, and also state number 3. So in terms of data given, we have T1 equal to 14 degrees Celsius equal to dry bulk temperature for state number 1, psi 1 relative humidity equal to 100% because the condition for the state number 1 in terms of air is saturated air. Volume flow rate V1 dot equal to 50 meter cubic per minute, and the pressure of the air is 1 atm, so we can use psychometric chart to determine the important parameter or value. T2 equal to 32 degrees Celsius equal to dry bulb temperature for state number 2. Relative humidity for state number 2 equal to 60%. Volume flow rate for state number 2 equal to 20 meter cubic per minute. And we need to use psychrometric chart in order to determine the parameter for state number 3, the condition for the mixture, where we can find we need to find the value of omega 3, relative humidity psi 3, dry bulb temperature TdB3, and also volume flow rate for the mixture V3 dot. Okay, now based on the data given, if we need to use the data given and also the psychrometric chart in order to determine the important parameter for state number 1 and also state number 2. So as I mentioned before, for each state at least we need to have 2 data in order to obtain the specific intersection point. Okay, first we look at the state number 1. Okay, for state number 1 we have the dry bulb temperature at the state number 1, where the temperature of T1 equal to 14 degrees Celsius, and we have the second information where we know that the air is saturated air, so the relative humidity for state number 1 is equal to psi 1 equal to 100% or 1.0. So we will have first intersection point that represents state number 1. Okay, so from this point, from this intersection point for state number 1, if we draw the line that a line that aligns with the enthalpy axis, so we can determine the value of H1, where the value of H1 equal to 39.3 kJ per kg dry air. So if we draw the horizontal line through the intersection point, so we'll get the value of omega 1, specific humidity for state number 1, and the value will be omega 1 equal to 0.010 kg H2O per kilogram dry air. So we need to read the value from the specific humidity axis. And also we can determine the specific volume for state number 1, V1. So we need to draw the line that parallel to the constant specific volume line. So the value will be in between 0.82 and also 0.83 meter cubic per kg of dry air. So we need to you need to make your own scale in order to obtain the exact value of V1. So V1 value will be 0.826 meter cubic per kg dry air. Okay, so now we look at the point for state number 2. So we have the data in terms of dry bulb temperature for T2 equal to 32 degrees Celsius, and we have the second data in terms of relative humidity psi 2 equal to 60%. So now we have second intersection point that represents state number 2. So from this point we draw the line for enthalpy. So we read the enthalpy value at the enthalpy axis. So the value of H2 equal to 79.0 kJ per kg dry air. Okay, from the intersection point for state number 2, draw the horizontal line, intersect with the specific humidity axis. So we'll get the value for omega 2, where omega 2 equal to 0.0182 kg H2O divided by kilogram dry air. And also we can determine the value of V2. So the value will be in between 0.88 and also 0.89. So make your own scale, so you will obtain the exact value for V2, where V2 equal to 0.889 meter cubic per kilogram dry air. Okay, so this is how you can determine the important parameter for specific state by using the psychrometric chart. Okay, so now for the mixing process, the state of the condition or the location of the state number 3 that refer to the mixture condition at the outlet of the mixing section. So we just draw a line that connect between state number 1 and also state number 2. So state number 3 will be in between state number 1 and also state number 2 on the on the same line that connect state number 1 and also state number 2. Okay, but now we cannot determine yet the exact location of state number 3, so we need to have at least one data to obtain the insertion point for state number 3. Okay, now so we need to determine based on the information that we have for state number 1 and so state number 2. So now we need to determine the value of omega 3, psi 3, and dry bulk temperature for state number 3, and also volume flow rate for state number 3. So for state number 1, we already determined the value of H1, where H1 equal to 39.4 kJ per kg dry air, omega 1 equal to 0.010 kg H2O per kg dry air, specific volume V1 equal to 0.826 meter cubic per kg dry air. For state number 2, so we also already determined by using the psychometric chart, where H2 equals 79.0 kJ per kg dry air, omega 2 specific impurity at state number 2 equal to 0.0182 kg H2O per kg dry air, and specific volume for state number 2 V2 equal to 0.889 meter cubic per kg dry air. So state number 3, we do not know yet the data, so we need to find another value in order to obtain the insertion point on the psychometric chart. So for state number 3, we need to determine omega 3, H3. From this value, we can determine dry bulk temperature TDB3, relative humidity psi 3, and also the specific volume for state number 3 before we determine the volume flow rate for the mixture. Okay, so now we need to implement the equation that we have learned in terms of the equation for the mixture, where we have the mass flow rate ratio, the relationship between mass flow rate ratio with the specific humidity difference ratio, and also the enthalpy difference ratio. Okay, so in order to use this equation, we need to determine the mass flow rate ratio MA1 dot divided by MA2 dot, where we know that MA dot formula equal to V dot divided by specific volume V, small letter v. So MA1 dot equal to 50 divided by 0.826 will be equal to 60.53 kg per minute, and for MA2 dot will be equal to 20 divided by 0.889 equal to 22.49 kg per minute. So divide this equation, so we'll get the ratio for mass flow rate MA1 dot divided by MA2 dot equal to 2.69. Okay, now let's say we want to use the equation for mass flow rate and also the enthalpy difference ratio in order to determine H3 first. Okay, so we will get 2.69 equal to H2 minus H3 divided by H3 minus H1. So rearrange the equation, so we'll get the equation for H3, where H3 equal to H2 plus 2.69 multiplied by H1 divided by 3.69. Substitute all the value that we have, so H3 will be equal to 50.1 kilojoule per kg. Okay, so now we need to use this enthalpy value. So we have one value for state number 3, so this value is enough in order to obtain the insertion point for state number 3 on the psychrometric chart. Okay, so now based on the value of H3, so we draw the line for the H3 equal to 50.1 kJ per kg. So now we have the third insertion point that represents state number 3. Okay, So from this point we can determine the important parameter for state number 3. If we draw a horizontal line through the intersection point for state number 3, so we will obtain the value for specific volume omega 3, where omega 3 equal to 0.012 kilogram H2O per kilogram dry air. And then if we draw a vertical line through the intersection point for state number 3, so we'll get the dry bulk temperature for state number 3, TdB3, which is equal to 19.3 degrees Celsius. And we draw the line that parallel with the constant specific volume line, so we'll get the value for V3, where we need to make you need to make your own scale, so you'll get the exact value for V3 equal to 0.845 meter cubic per kg dry air. Okay, so the last one, we need to draw the curve for relative humidity through the intersection point for state number 3. So we'll get the value for relative humidity is around 88%. Okay, now state number 1 will be complete to obtain the value of enthalpy, omega, and also specific volume. Similarly with state number 2. For state number 3, at the beginning we already calculate the value of H3, where H3 equal to 50.1 kJ per kg. Based on this value, so we implement this value to the psychrometric chart. Then we already determine the value of omega 3, where omega 3 equals 0.012 kg H2O per kilogram dry air. And then the dry bulk temperature for state number 3 equal to 19.3 degrees Celsius. Relative humidity psi 3 equal to 0.88 or 88%. And also we obtain the specific volume for state number 3, V3 equals 0.845 meter cubic per kg dry air. So from the question, so we will answer three question out of 4 questions. So we already obtained the omega, dry bulk temperature, and also relative humidity. The last one, we need to determine the volume flow rate for state number 3. So we need to manipulate the value of specific volume that we obtain from the cyclic chart. So we know that for the mixture, in terms of mass flow rate of dry air, MA1 dot plus MA2 dot will be equal to MA3 dot. So we already have the value of MA1 and also MA2 dot. So just add both value. So we'll get the value for MA3 dot, where MA3 dot will be equal to 83.02 kg per minute. So we know that the equation for volume flow rate, V3 dot will be equal to MA3 dot multiplied by specific volume for state number 3. So substitute all the value, so we'll get volume flow rate V3 dot will be equal to 70.1 meter cubic per minute. Okay, that's all for chapter number 6. So here in this slide, I already list down numbers of questions that can be used for your exercise. Okay, so this question based on the thermodynamic textbook by Yunus Chengel, 7th edition. So if you have time, so you can find the answer for this question, as your exercise for the final examination. Okay, that's all for chapter number 6. Assalamualaikum warahmatullahi wabarakatuh.